So here we are moving into Unit 6, and we're going to start with Chapter 23, which is on inferences about means. Now, you might be saying, we just spent an entire unit talking about proportions. Well, that was all focused on categorical data. And now we're moving on to quantitative data. So as you can expect, we're going to do hypothesis quantitative data. And we're going to be doing hypothesis tests and confidence intervals with means and standard deviations. So, just like before, we have our homework problems. Check Schoology to understand the pacing for this. I'm going to do my best to break these down into small enough video chunks that it's doable over the course of a week, just like we would with our lectures. So, the objective for this chapter is students test null and alternate hypothesis about a population mean. So, as you know, now that we're familiar with creating confidence intervals and testing hypotheses about proportions, we should be able to do the same thing for means, and it should be very easy. And as we know, it's still true that confidence intervals and hypothesis testings are based on sampling distribution. Remember, as n increases, our distribution, a sampling distribution gets closer and closer to normal. Usually when n is greater than or equal to 30, that's when we have a normal distribution, regardless of skew. So the only real change is that the central limit theorem tells us the sampling distribution for sample means is normal with a mean of mu. Remember, our symbol is mu. And our standard deviation for our variable, we have y bar, is equal to sigma over the square root of n. That should look pretty familiar. So all we need to do to proceed is a random sample of quantitative data. Oh yeah, and the true population standard deviation, sigma. That sigma part is going to be a problem. Now, you might ask, why is that an issue? Well, proportions have a link between population proportion value and the standard error of the proportion sampling distribution. But that's not the case with means. Knowing a sample mean tells us nothing about the standard deviation of that sample or the standard error of a sampling distribution of the mean standard deviation with x bar. So what do we need to do from there? Well, we're going to use what we have available. So we will estimate the population parameter sigma, which again means standard deviation. We use Greek letters to denote that, with a sample statistic, S. So S is the standard deviation for our sample. With our resulting standard error for our given random variable, y bar is equal to S over the square root of n. Now, if we are using the sample's standard deviation, we have just added additional uncertainty or variation in our standard error from S, which is most likely not equal to the population standard deviation. So we need to allow for the extra variation so that doesn't mess up the margin of error and the p-value, especially for a small sample. Additionally, uncertainty alters the shape of the sampling distribution. The distribution is still unimodal and symmetric, but it's no longer normal. At least, not the normal with which we're familiar. So what is this sampling model? So this is where students' t distribution comes into play. So this guy, William S. Gossett, he comes to our rescue. Now, fun fact, Mr. Gossett was an employee of the Guinness Brewery in Dublin, Ireland, who worked out what the change to the sampling model was and how we might deal with the added variability. So the sampling model that Gossett created, he called the students T. Now, if you're wondering why it's called T and not G or Gossett, well, Guinness would not allow employees to publish data from the brewery. So Gossett published his findings under the pseudonym student, hence students T. So the students T models are a whole family of related distributions that depend on a parameter known as degrees of freedom. So we denote degrees of freedom as df, or the Greek letter mu. So the letter after mu, which is pronounced mu for mean, is the lower cases mu, which is NU, which is why that's written there. I'm going to use these interchangeably in the notes. And the test statistic that we use, so instead of a z-score, we use t with an underscore of degrees of freedom. When appropriate, the t statistic replaces the z statistic in calculations. So, a sampling distribution model for means. We have t equals our sample average minus the population average all over the standard error of our random quantitative variable. So when the conditions are met and the standardized sample mean follows student's t-model with n minus 1 degrees of freedom, get used to seeing that all the time. To find degrees of freedom, we take the sample size and then we subtract 1. We can estimate the standard error with SE of our random quantitative variable. S, again, S is standard deviation of our sample. And N is our sample size. So this is how we find this formula to find our standard error to calculate our t value. So one sample t procedures are to be used only when the population is sufficiently normal. So it must be reasonable to assume that the population, our sampling distribution, is sufficiently unimodal and symmetric in order to justify the use of t. The t statistic is strongly influenced by outliers. So as a result, it's imperative that you check the data. If the population is not unimodal and symmetric, I just need you to understand those, not unimodal and symmetric, there are outliers and the sample size is small, the results will not be reliable. Not be reliable. And we have to find other statistical methods. So the simplest way to verify the population is sufficiently normal is to trust your methodology. Assume the sample is representative of the population and verify that the sample is sufficiently unimodal and symmetric by making a histogram of the sample. I'm going to show you guys how to use your graphing calculators to check as we do a couple examples later on. So the question becomes then, when to use the t procedures. So I and your calculator have a simple rule for using t over z. Here it is. If you do not know the population standard deviation, if it's not given, use a t statistic. However, keep in mind that it's not always appropriate to use the t model. And this is due to the central limit theorem. So to ensure a sampling distribution warrants using the normal model, we must verify the sample sizes are appropriate. So I want you to get used to the numbers 15 and 40. If the sample size is less than 15, only use t procedures if the data are really close to normal. It must be a reasonable assumption that the population distribution is normal. It must be reasonable. If your sample is between 15 and 40, use t if the data is unimodal and reasonably symmetric. And you can verify this by a histogram of your sample. And finally, if the sample size is at least 40, you may use t procedures, even if the original data is skewed. This is why the central limit theorem comes in handy. So as we collect more and more samples, as long as the sample size is at least 40, you can always use the t procedures. When Gossett corrected the model for the extra uncertainty, the margin of error became bigger. So confidence intervals will be slightly wider, and p-values will be a little larger for t models than they were for the normal model. Using the t model compensates for the extra variability introduced by estimating the population parameters with the sample statistics. Now, if you need a further explanation, I highly suggest watch a few of the Khan Academy videos on AP Stats for a further explanation. So, if we were to construct a confidence interval for one sample t interval for the mean, when the conditions are met, we can find the confidence intervals for the population mean mu, exactly like we did for proportions. So our confidence interval, we will write our sample average plus or minus the critical value. So this is our critical value, No, denote t n minus 1. That gives me my degrees of freedom. We always indicate that with our critical value, and then we have multiplied by our standard error. You can also write it, if we plug in the formula for standard error for our random variable, x bar plus or minus t star with n minus 1 degrees of freedom times the sample standard deviation over the square root of n. The critical value depends on a particular confidence level, C, that you specify on the number of the degrees of freedom. So once you figure out your confidence level, you also will then go to a chart, or we can use our calculator to determine what the critical value is. It's not as simple as the 3 numbers that we had for critical values for Z statistics. So the T distribution has the following properties. Students' T models are unimodal and symmetric, just like the normal model. So that's nice. The mean of the distribution is equal to 0, just like the Z distribution. So both of those match. The difference between the T curve and the Z curve, which should be pictured here, is the standard deviation. Both the distributions have a mean of 0. The distribution for a Z distribution is a variance of 1, where the T distribution, the variance is approximated by nu over nu minus 2. Again, these are talking about degrees of freedom. But T models with only a few degrees of freedom are lower and have much fatter tails. Like someone sat on the top of a Z curve and just squashed it down, making the margin of error larger. The variance for T is always greater than 1. So again, the variance for T is always greater than 1. Although as the degrees of freedom increases, and in fact, as it goes off to infinity, it's getting closer and closer to the normal model, so the variance will approach 1. Here, again pictured before, but just as another picture, is an example in green of the normal model. Both have the same mean, centered at 0, but the normal goes higher and lower quicker. Versus, depending on the degrees of freedom, you're going to get a bunch of curves for the T distribution. So, as the degrees of freedom, which is dependent, remember degrees of freedom is equal to n minus 1, so it's dependent on the sample size. As the degrees of freedom increases, the T distribution gets closer to the normal distribution. And since the standard deviation for the sample gets closer to the population, because our n is getting closer to our population by sending it to infinity. In fact, the T model with infinite degrees of freedom is exactly a normal. So these should look somewhat familiar, but we're going to talk about the assumptions and conditions. So let's just go through a normal population assumption. We can never know if a population is truly normal, but we can make a reasonable assumption about some populations. So what is the nearly normal condition? The data come from a distribution that is unimodal and symmetric, that is known, or we can show that from a histogram. So we always check by making a histogram, or if you remember, we can also make a normal probability plot. I'll show you both of those in an upcoming video of the sample data. If the sample is representative and the sample is sufficiently unimodal and symmetric, we conclude that the population and the sampling distribution are sufficiently unimodal and symmetric. I mean, this should come as no surprise to you. So what else do we check? The independence assumption. So independence condition, the data values should be independent. Randomness condition, the data arise from a random sample or randomized experimentation. And then the 10% condition, which allows for without replacement. When a sample is drawn without replacement, the sample should be no more than 10% of the population. Now, the one other check that we looked for is NP and NQ with proportions. So what is the sufficient sample size condition that we need to check for a T distribution? So sufficient sample sizes requires considering the sample sizes of 15 and 40. If we cannot reasonably assume the distribution of the population is normally distributed, then we must check further. So remember this. with our nearly normal condition. The smaller the sample size, think lower than 15 or so, the more closely the population data should follow a normal model. If it doesn't, then we're done. For moderate sample sizes, think between 15 and 40 or so, the T works well as long as the data are unimodal and reasonably symmetric. It doesn't have to be perfect, but just reasonably symmetric. So we're going to check the sample distribution with a histogram. For larger sample sizes, think n is greater than 40, the T statistic is acceptable to use unless the data are extremely skewed or has significant outliers. So how do you find the critical value either by hand or with a calculator? So with students' T model, it's different for each value of degree of freedom. How do you find the probabilities? How do you find the value? So statistics book, which you can see in the back of yours or on the document that you would get from the AP test, it would look something like this. As this descends down, so this is our degrees of freedom, which comes from n minus 1, and then we have our tail probabilities. So as this decreases down, you'll see the last line will be infinity. We have our tail probabilities, which may look familiar. And at the very bottom, you're going to get a confidence interval. So you can see which numbers relate to our distribution. Now, if you remember, we always use alpha over 2 to figure out our confidence interval, and we've seen this before. Of course, we also have our calculator to use. So how do we calculate this statistic? As always, with any test statistic, we use the observed value minus the expected value over the sample standard deviation. So for a t value, it's the sample mean, which is x bar, minus the population mean, which is mu, over the adjusted standard deviation, which is our standard error, s over the square root of n. We will always denote with a t statistic what the degrees of freedom is. So we write df n minus 1, always after it. So if you're calculating a confidence interval, it's exactly the same thing as a z statistic. Simply replace z with t. So I will take either, and I'll probably use the latter one first, but we have our average, sample average, plus or minus our t statistic. This is our critical value, and this is our standard error for x bar. Same thing. We have x bar plus or minus t, indicating degrees of freedom, times s over the square root of n. This will give you your confidence interval. So for example, if we want to find a 90% confidence interval for the population mean, if a sample of 20, that's our n, has a mean of 1462 with a standard deviation of 42. Sorry, this is our x bar. So this is the calculator practice. So I'm going to show you how to do this. So we'll forego the assumptions and conditions, plus these numbers have no context. So to find the t critical value, we're going to use, or t sub 19. We're going to go to the calculator. We're going to use inverse t. We want a 90% confidence interval, so we use alpha over 2, 1 minus alpha over 2, which gives us 0.95. That's our standard normal way of calculating inverse normal scores, one-tailed test, comma, the degrees of freedom. If you do that on the calculator, which you can see, we get 1.729 da 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 da. So then to find our 90% confidence interval, we take our critical value times our s, which in this case was 42, over the square root of 20. And if we multiply those two, we get approximately 16.2. So our 90% confidence interval would be thus 1462 plus or minus 16.2, or from 1445.8 to 1478.2. Last up, you may notice that if you're finding a interval, it's going to ask you Either do you have data that you want to use, or are you using statistics? We will go through both of these examples. Last bit for this video. To find a critical value, just to use your calculator, to find t star, you're going to use inverse t, and then we're going to use either 1 minus alpha. This would be for a one-tailed test, or 1 minus alpha over 2 if this is a two-tailed test. Most of the time it's a two-tailed test, so we would use this one. Comma, degrees of freedom. To find the area below, we use TCDF. To find area between, TCDF for above. Each of these are going to be your percents. So hopefully this is a good start to the first video. We're going to pick up with going over another example of confidence intervals and then hypothesis testing with t-statistics.